Hello and welcome to the InterPlex. I recently had the privilege of speaking to Constantino Tsallis at his beautiful home in Rio de Janeiro. Tsallis is a theoretical physicist focused on non-extensive statistical mechanics, and he's also a pioneer in complex system science research. He's perhaps best known for discovering a non-additive entropy, which is a generalization of the Boltzmann-Gibbs entropy. It's now commonly referred to as the Tsallis entropy. This framework has led him to many theoretical investigations and interdisciplinary collaborations, from critical phenomena, chaos, nonlinear dynamics, cognitive psychology, astrophysics and high-energy physics, immunology, neuroimaging, economics, and the list goes on. It's just really fascinating how these frameworks can be applied to so many different phenomena. He has been a researcher at Brazil's CBPF for over 40 years. He's been an invited lecturer all around the globe. He's an external professor of the Santa Fe Institute. He's a former close collaborator of Murray Gell-Mann, who in the physics community is one of the heroes. And he's just an incredibly fascinating individual to speak to, and has a lot to teach the world and ways of doing research with a very broad perspective, though with a lot of rigor. So I began by asking Tsallis about his background. He was born in Greece, grew up in Argentina, has lived for quite a while in Brazil, been all over the world when studying and researching. So I wanted to know how those cultural influences impacted his way of thinking outside the box and discovering such a broad framework for doing science. Well, thank you very much for having me here in your lovely home in Rio de Janeiro. Constantino, it's really nice to be here with you.
My pleasure.
So let's start with a little bit of a personal history. Something I've been curious about. Do you think your diverse cultural background, has helped you in any way to be, let's say, an outside-the-box thinker, innovative in different aspects with your work? Maybe you can talk a little bit about your history, where you come from, and then how it might have led into some of your work.
Well, I was born in Greece, in Athens, and after the Second World War, my father brought our family to South America. And basically we established in Argentina, Mendoza, which is the land of the good wines in Argentina.
Oh yes, I know it well.
You know.
Maybe too well.
Maybe too well. And after that, I went to Paris to do my doctoral degree. I lived 8 years in Paris, and after that I came to Brazil in 1975, and I live in Brazil since then.
Great. What brought you initially? Was it a faculty position or research position to Brazil?
Well, I started as a full professor in the University of Brasilia, where I stayed 2 years. And then I came to CBPF, Centro Brasileiro de Pesquisas Físicas, where I am until now. Along the years, I started in a certain position, and as decades go on, they made me emeritus. There is a funny thing that happened with this emeritus position. They made me twice emeritus. Why? Because a director has made me emeritus, and a few years later, another director wanted to make me emeritus, and he didn't know that I was already emeritus. And in the middle of all the people, he said, so now I will give you the degree of emeritus. And I felt that it was not very polite, in that moment in front of everybody to tell them, but I am already emeritus. So I accepted the plate again. So I guess...
Was he embarrassed afterwards of this mistake?
I don't think I ever told him.
Oh, okay.
Yeah.
All right. Well,
Yeah.
in terms of some of the professional history, what you're very well known for is this generalized non-additive entropy in statistical mechanics. Maybe you can explain a little bit more about what non-extensive statistical mechanics is. But again, your personal history, it would be good to draw on where you think these insights came from. Were they professional collaborations, cultural, different ways of thinking about things?
I think that indeed there is a cultural influence.
Yeah.
Because I have had, along my life, 4 cultural influences: the Greek, the Argentinian, the French, and the Brazilian. Mm-hmm. And they are so different among them that I guess the crossing of all these ways of thinking, mm-hmm. of acting, of doing research, and of living, I think they have had some influence. In particular, because in the Greek culture, science is not separated from arts. Mm-hmm. So it's science and arts. So the paradigm of, or maybe the utopia of science is the truth. Mm-hmm. And the utopia of art is beauty. But since Plato, these 2 concepts of truth and beauty are handled together. And I believe this has had an important influence of my way of doing research.
Is that like a guiding principle for you? Beauty,
yeah.
Artistic application, maybe?
Not as a principle, but I do research in such a way that I see these aesthetical aspects, mm-hmm. and I follow them when they are very strong, because I believe that there is surely some truth if it is very beautiful.
Is this in the mathematics or the observation?
Everywhere. And in particular in the formulation of that non-additive entropy, okay. SQ, I wrote it in directly. I did not deduce it because it's a postulate, but I wrote it directly in a few minutes, and I thought it was very beautiful. So I said to myself, why not generalizing Boltzmann-Gibbs statistical mechanics upon this basis, which for the particular case Q equal 1 recovers the standard theory. And this is how it all started.
Was there a particular inspiration or people you were working with, or was this like a eureka moment that you had?
No, in fact, I was influenced by multifractals, mm-hmm. which is a generalization of fractals. And I was in a meeting in a French, Mexican, Brazilian meeting in Mexico City. And at a certain moment, there was a coffee break, and everybody went out to the coffee break, excepting me, who for whatever reason I stayed inside the auditorium. And there was a French professor that was explaining something to a Mexican student on a blackboard, far away from me. I couldn't hear what they were saying, but I could see what the French professor was writing on the blackboard. Mm-hmm. And he was in fact explaining to the Mexican student multifractals. And in the multifractals, it appears all the time, probabilities to a power, which is usually called Q. So it appears P to the power Q all the time in the well-known theory of multifractals.
Sure.
So he was putting expressions of this sort on the blackboard, and I thought it's funny, P to the power Q, so we are putting a bias on the probabilities. With this, we could generalize the entropy, and from that, generalize the Boltzmann-Gibbs statistical mechanics.
So it all just came to you in that
Yeah.
time when you were looking at it.
Yeah, yeah.
Interesting. And you
So
wrote-
after that, I just wrote it down and I published it.
Great. And you were already working in statistical mechanics. That was your...
Yes, I was working in statistical mechanics, yes.
And as I had mentioned, non-extensive statistical mechanics in relation to non-additive entropy. What is extensive statistical mechanics versus
Well,
non-extensive?
maybe it would have been a good idea to call it non-additive statistical mechanics instead of non-extensive statistical mechanics. But it is written non-extensive in thousands of papers, so I think it's too late to change it. But the first idea was that the primary physical systems that I had in mind was long-range interactions, like, for example, gravitation. And when you have long-range interactions, the total energy, which normally is extensive in the thermodynamical sense, this is to say proportional to n, the number of elements. When you have long-range interactions, it becomes super-extensive. It becomes non-extensive. And from that, I took the name non-extensive statistical mechanics. The entropy is non-additive, and you choose the value of Q in such a way that the entropy becomes extensive. Why? Because the mathematical nature of thermodynamics is based on the Legendre transformations. And in the Legendre transformation, you can easily verify that energy can be non-extensive, no problem, but entropy has to be extensive. Otherwise, you are going to violate the Legendre structure of thermodynamics. And up to now,
You needed to preserve that.
yeah, we need to preserve that. And the normal entropy, Boltzmann-Gibbs entropy, also called von Neumann entropy, for quantum systems, and engineers like to call it Shannon entropy, it's the same thing.
Yes.
That one, for those complex systems, is not extensive. Boltzmann-Gibbs is not extensive, but SQ with a unique value of Q is extensive in many of them. And that was the idea.
That was and I know you don't like to use this term, but this non-additive entropy has now frequently been called in your namesake Tsallis entropy.
Yeah.
Which, when I was in school, I remember reading about this. So it's really interesting to get an explanation. How
It's
did
generosity of my colleagues to call it like this.
well deserved? So how would you say this framework, this discovery, let's say, of the non-additive entropy, how did that get you involved in the early days of complex system science, in the growth of that as a field?
First of all, when I wrote down that entropy was 1985,
Okay.
but I only published 1988, 3 years later, because during 3 years I was trying to understand what would be the meaning of this Q parameter, the meaning of a non-additive entropy. And finally, I thought it was a good idea to publish it, so I did. But after that, during several years, it was not clear what would be good for this entropy. Until a remarkable paper by Plastino father and Plastino son, Ángel Plastino Sr. and Ángel Plastino Jr. from La Plata in Argentina, where they published a paper in which they analyzed consequences of Q not being 1 for gravitational systems.
That's where it started, in gravitational systems.
The physical applications, yes.
Okay.
Yes, gravitational systems, which of course are long-range interacting systems. And when they published this, I happened to be in Florianópolis, a city in the south of Brazil, in a meeting, and in that meeting happened to be a very good friend of mine, which left us, Roger Ménard, from Grenoble, France. And with him, we discussed several hours walking around why this application of Plastino and Plastino worked so nicely with Q statistics. And at the end of this lengthy discussion, we arrived to the conclusion it is just because gravitation has long-range interactions. It comes from there. So that opened a door that has been very important in all these applications.
Yeah, right. Did you ever imagine that there would be so many different applications of?
No, certainly not.
We'll get into that later. So, I mean.
Yeah, it's impossible to imagine that when.
But at that time, it hadn't occurred to you that there could be like so many disciplines incorporating this kind of.
No, it didn't came to my mind. It didn't come to my mind, but it happened so. So today there are almost 11,000 of papers of something like 17,000 scientists around the world that use this concept of non-additive entropy and non-extensive statistical mechanics as an important ingredient of their own papers.
Yeah, it's really amazing. Well, let's go back again to these, just to get some of the historical context, these early days of complex system science as well. I know you were associated with the Santa Fe. You had collaborations with some very well-known physicists like Murray Gell-Mann.
Yes.
What had him take an interest in your work? Maybe you can describe some of this context.
Well, this happened, in fact, in a meeting, in a Gordon conference, north of Pisa.
Okay.
In that meeting, the Gordon conferences are quite peculiar because practically only invited participants can be there. It's not the sort of thing, at least it was not the sort of thing where you could register and go there. No, you had to be invited. So they were very closed meetings. And in that occasion, Murray Gell-Mann was there as well. And after his talk, etc., at a certain moment, I gave my own talk. And I presented SQ and the consequences of that. And when I finished and I was putting together my slides, it was the time where you presented things through view graphs, not through PowerPoint or similar ones like today.
What year was this, the Gordon Conference?
That was it's a little place north of Pisa. I can check the name, but I think it was Ciccio. I would have to check it.
But what year? Do you remember?
Yeah, it was Well, I have it here. I can give you the exact name and the exact date, but it was something like 1999 or something like this,
Right.
or 2001, something like that.
That's when you first met Gelman.
Yes,
Okay.
yeah. Because when I finished my talk, and as I said, I was just collecting my slides, he stood up in the bottom of the auditorium and he came down the stairs and saying, "Wonderful." And everybody was very perplexed. The mythical Murray Gell-Mann calling a presentation wonderful. And when he came close to me, I said, "Thank you very much. It's a honor coming from you." And then he repeated, "Absolutely wonderful. You must give me a paper of yours on this right now. I have to read something about that now." So I gave him an article that I happened to have in my hands. And since then we became related. And so he invited me to spend, at the end of the story, more than 2 years, 2 years and a half, at the Santa Fe Institute. And this is when our work together.
Before that, how had been the acceptance of non-additive entropy? Was it something?
Controversial.
Yeah.
There were people like Joel Lebovitz and Itamar Procacia who were saying that that was the most stupid thing to propose, a non-additive entropy. But on the other side, there were people like Kadanoff and Eddie Coyne and many others, important physicists, that were very interested by that. And they were supporting and they were inviting me to give talks in Chicago and in other places, at Rockefeller University, to understand better the idea. With Eddie Coyne, we had 4 hours conversations about what is the physical meaning of this probability power Q. And another important support came from MIT. Well, his name escapes me in this moment, but I can give you easily. And he was also very fond of that.
That helped to gain more general acceptance.
Yes, yes. Through this kind of people, it
helps.
It helps a lot.
Of course.
For example, the famous Laszlo Tisza, who was professor at MIT. At that time, he was retired. But Gene Stanley from Boston University arranged so that we had a long discussion, Laszlo Tisza and myself. He was very old at the time, but he was very lucid. And at the end, he told me, "That's very cute. I stopped working in statistical mechanics because I didn't know which way to go. And it certainly never came to my mind to generalize the entropy." And a few days later, his well-known book, Generalized Thermodynamics, he wrote a dedicacy to me with best wishes to Constantino and his bold enterprise to generalize thermodynamics. And when I showed this book to Tom Kaplan in Michigan, where I was spending a sabbatical year, he had been, Laszlo Tisza had been supervisor of him And he told me, "Oh, you must cherish this book very much." And indeed, I cherish it very much.
I imagine so.
Yeah.
That's great.
Laszlo Tisza was the professor of Cullen, and the book of thermodynamics of Cullen, it's one of the best textbooks on thermodynamics. So Cullen learned thermodynamics from Laszlo Tisza.
Great. And these were all great steps for you to get more understanding and
Yes.
exposure of your
Absolutely, yes.
Was it after the work at Santa Fe that you founded the National Institute of Complex Systems here in Brazil, or when was that?
Yeah, I think it was roughly, but close to when I came back
From there?
from Santa Fe.
Early 2000s, something like that? Or?
2006.
Okay.
In Santa Fe, the Air Force Research Laboratory had hired 3 or 4 senior scientists to work with me to learn the details about this entropy. And they had also hired 3 or 4 young scientists as well. I never asked what for, but probably the young scientists were doing applications that were of interest to the Air Force. But the senior ones, which is the ones who are the ones with whom I interacted, they behaved and discussed freely, and we published several papers together, and it was very, very nice.
Great experience. Certainly.
At the end of that, they asked me if I wanted to stay longer in United States. I said, not now. Now I have to go back to Rio de Janeiro. And then I left and came back to Brazil. And 1 or 2 months later, the Air Force fired all those senior scientists, telling them, "You were hired to work with Tsallis, but Tsallis is not anymore in the United States."
That didn't work out so well for them. That didn't work out so well for them.
Well, they had to find new jobs.
Of course, yeah. But did you have in mind at that time that you wanted to bring this new science to Latin America, to Brazil, to kind of get your colleagues in Brazil more involved in different applications of complex system science?
Well, I was working on that, so it would be natural that I would involve the collaborators of mine.
Outside of this one curiosity I have, maybe you have some inside information about why quarks are called quarks. Did you ever find out from Gell-Mann?
Oh, yes. Yes, it is known. It's from the book of, it has inside in one of his books, something like quark. And then Gell-Mann thought, oh, quark, oh, let's call it quark.
Okay, that's it. All right, so there's not any etymology or something. It came from
No.
was inspired.
It's a kind of funny word
Yeah, sure.
that is in the book.
I remember discussing that with my colleagues back in school, so I thought I'd ask you.
Yeah.
So it comes from a book. All right, well, maybe let's shift a little bit towards some of the research and how complex systems and non-additive entropy have sort of fostered this diverse spectrum of interdisciplinary collaborations. I mean, in your case, which is quite an inspiration, there's high energy particle physics, cold atoms, economics, astrophysics and cosmology. I could go on and on. Cognitive psychology, immunology, cancer, and neuroimaging. It's just kind of amazing for me. I find it very inspirational that some of these fundamental principles can then form the bridge between so many different disciplines and ways of thinking, and much of what I'm working on is
it's quite amazing, in fact, to me as well.
Urbanization, population evolution. Anyway, so it goes on and on. So what are some of the core aspects of the frameworks of complex systems science, and specifically non-additive entropy that make this even possible? Is it non-linearity? Is it concepts of emergence, scale invariance, self-organization? I mean, what is it that makes this even possible?
The correlation, the relevant correlations in the system, if they decay not exponentially, but super exponentially, typically like a power law, that changes the whole thing about statistical mechanics.
Okay.
Because an exponential decay, it has all moments finite. The first moment of an exponential is finite. The second moment is finite. The third moment is finite. All moments are finite. But when you have correlations that decay like a power law, only the first momenta are finite. The higher order momenta, which can be the second, the third, the fourth momentum, they diverge. And that makes an explosion within the legitimacy of Boltzmann-Gibbs statistical mechanics.
Okay.
The mathematical assumptions, which are either implicitly or explicitly used in Boltzmann-Gibbs statistical mechanics, many of them explode. Instead of giving you finite quantities, they give you infinite quantities, and therefore the theory doesn't work anymore.
So
when you put Q into the game, it transforms infinities in finite quantities, like the regularization that Feynman did for electrodynamics, where he had singularities, divergences, and appropriately handling them, they were giving finite quantities. So the theory is said to be regularized. In some sense, Q statistics is a regularization for Boltzmann-Gibbs statistical mechanics, where it explodes, where it doesn't work.
But in addition to getting finite properties, where before they were divergent, are you detecting common patterns between these different fields using Q statistics? Are numbers or data that actually correlates one, an underlying principle that shows how these are bridged?
For example, in time series of a system, and basically all physical systems, some of their properties are described by time series. When you look at the fluctuations that appear in time series, the fluctuations in the typical Boltzmann-Gibbs systems are like this. Roughly like Gaussians, random walk behavior. But when you have complexity, those fluctuations, typically they are like this. It jumps, or it jumps down, and jumps again. So when I see that in a system you have fluctuations that jump up suddenly or down, and on top of that, the jumps tend to cluster together. So it jumps, 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 and then it doesn't jump. And then again, jumps, 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 and then it doesn't jump. When I see this, I can easily bet non-additive entropies are going to describe correctly this system.
What do those jumps represent exactly?
It's kind of moments in the time series where correlations cluster together in such a way to produce a very big effect that does not exist when correlations decay exponentially quick.
With non-additive. Yeah, I wonder, well, one thing I was going to ask you to describe is also what is meant by the edge of chaos.
Edge of chaos. Very interesting, dynamical situation. In many systems, you have very chaotic behavior and changing some parameters. The strong chaos disappears and it appears regular orbits, something easy to predict, like a cycle 2, up, down, up, down, up, down. Not a big mystery. But in between the strong chaos and the stable orbits, very frequently at the edge of chaos, you have weak chaos, not strong chaos. And the quantities that are relevant show a power law behavior instead of an exponential behavior. And when this happens, this is exactly the place where non-additive entropies work very well. Boltzmann-Gibbs entropies work magnificently well, as 150 years of successes have proved, when you have strong chaos. But at the edge of chaos, you have weak chaos, and then it doesn't work anymore.
Is this where the fractal structures are applied as well?
Exactly. Because a language is at the edge of chaos. Economics is at the edge of chaos. Earthquakes are at the edge of chaos. For example, for a language, in the chaotic region, I would say ba, bl, bz, z, tak, ting, tong, tak, something like this, very chaotic. And you understand nothing, and we cannot communicate. On the other side, where you have a stable regularity, I would say blah, 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 blah. Very easy to predict what I'm going to say next. I'm going to say blah. But we cannot communicate. So for having a complex communication between humans, you have to be in the frontier between the extreme chaos and the very regular behaviors. In that frontier is where biology emerges, where economics emerges, where complexity emerges.
Is this related to criticality and phase transitions as well?
It is related to that, yes, very much.
So at those points of criticality, is that where non-additive entropy is?
Yes.
Well?
For example, one example in which it has been possible to analytically calculate Q is the critical point of one-dimensional Ising model and similar ones in the presence of transverse magnetic field.
Okay.
At any finite temperature, because it is one-dimensional, there is no phase transition. But at zero temperature, there can be a phase transition, which is a quantum transition. That quantum transition appears for a specific value of the transverse field. And in that particular point, at the time he was a younger student at the Scuola Normale Superiore di Pisa in Italy, Filippo Caruso and myself, we published the analytical expression of Q. And there was an interesting step, because it's not easy to have analytical expressions for Q. It's in fact very, very hard. But in that example, that kind of systems, it was possible to calculate them. And by the way, I was telling you about the contributions of Ayrton Deppmann from São Paulo for high energy collisions, where CERN has again and again and again found many collisions whose transverse momentum distribution is characterized by Q equal to 1.14, and that specific value remained an enigma during many years. We knew that it was that value, and it was checked again and again experimentally in CERN, in Brookhaven, and elsewhere, but we didn't know why, until an important paper by Ayrton Deppmann gave an analytical expression for Q in terms of the number of flavors and the number of charges that you have in the quarks. And when you put in that little formula of him and collaborators, when you put the numbers 6 and 3, it gives you Q equal 1.14. So
the explanation from first principles.
Yes, from first principles.
Fascinating.
Yeah, very interesting. After that, there was another value for Q, which was 1.11 instead of 1.14. That was published by Rafalski, and a student of him at the time. And again, why in these experiments they find Q equal 1.14, and in that paper, a physical regulator that Rafalski published long ago, it was 1.11. And in the formula of Ayrton Deppmann and collaborators, if instead of putting 6 and 3, you put 3 and 3, you get 1.11. It was fantastic.
Can you speak in a bit more detail about some of these experimental results that have come out that have used Q statistics to quantitatively?
Well, one example that is in those areas that are sort of bizarre is the case of in cosmology, the entropy of a black hole. And the entropy of black hole, which appears again and again in the literature, is the Bekenstein-Hawking entropy, which instead of being proportional to the volume of the black hole, it is proportional to the area, which makes that entropy, Bekenstein-Hawking, to violate thermodynamics, because it violates the extensivity of the entropy. And maybe 10 years ago, I was invited by Antonino Tsallis in a meeting, in a very interesting meeting, with maybe 15, 20 participants, among them a couple of Nobel Prizes, at the Pontifical Academy of Science in the Vatican. So, with one of the invited speakers, it came out this problem that the Bekenstein-Hawking entropy violates thermodynamics because it is not extensive. During those evenings, we were hosted at this hotel, Saint Martha Hotel, which is inside the Vatican, which is where the Pope lived sometime, maybe even today, and where the cardinals that gather to choose the new Pope where they live. So we were hosted there. And during the evenings, as you can imagine, an evening inside the Vatican is not particularly exciting. And so I was thinking, what would be the value of Q, which would make the entropy of a black hole to be extensive, and which for sure was not Q equal 1. So I tried again and again several paths, and suddenly I realized that there was no value of Q that would solve that problem. So it was not related to the Q entropy. So I proposed a different entropy, which is called delta entropy instead of Q entropy, and which people also refer to with my name, perhaps without knowing that these are two different entropies. And this delta entropy has this delta parameter, and when you put delta equal 1, you recover Bekenstein-Hawking entropy, but it is non-extensive. And we published in 2013 a paper where we showed that delta equal 3/2 instead of 1 recovers extensivity of the entropy and therefore satisfies the Legendre structure of thermodynamics. So since that time, I'm saying the Bekenstein-Hawking entropy is fine, but it is not the thermodynamical entropy of a black hole. It is the Boltzmann-Gibbs entropy of a black hole, but it's not the thermodynamical entropy, because it violates the Legendre structure of thermodynamics. But delta equal 3/2 instead would solve the problem. And during the recent two, maybe 3 years, there has been several papers have been published using cosmological data, and all of them are close to 3/2 and definitively far away from delta equal 1. So that shows that non-additivity is a broad concept that can solve things not only for the Q entropy, but using, for example, the delta entropy, and maybe some others entropy, I don't know. But for sure, SQ and S delta are very interesting, and they in particular explain these data from cosmology, from the observations of neutrinos and dark matter in cosmology.
Quite a foundational application there.
Yeah.
Now imagine what you would have accomplished if you lived in the Vatican and not Rio de Janeiro. Right? That's just one night there, right?
Yeah, maybe 3 nights.
3 nights.
Right now we have submitted a paper with Henrik Jensen, who is the leader of the group of complexity at Imperial College in London.
Jensen.
Yeah, Henrik Jensen. We have just submitted a paper in which we make a variation of the delta entropy, again with delta equal 3/2, and therefore again fits the experimental data in cosmology and neutrinos and that kind of things.
And what role does this have if it has any role in let's say, the black hole information paradox? Is there something that this is?
Well, that up to now we do not know how to make thermodynamical measurements related to black hole, because you wouldn't like to go nearby to see what happens. But if in some way or another it was possible to to measure thermodynamical properties, such as specific heat, magnetic susceptibility, equation of states, and things like this, those, if you use delta equal 1, which is Bekenstein-Hawking, my conjecture is that they will fail. And if you calculate them with delta equals 3/2, it will work. Which once again would strongly show that extensivity of the entropy, if additive or non-additive, but being extensive, is very, very important.
That cannot
Which
be
is-
violated.
It cannot be violated
creates all these kinds
from
of
what we
paradoxes.
know up to now.
I see.
I mean, classical thermodynamics, as you know, was declared by Albert Einstein in 1949 or 1959 as the unique physical theory that will never be overthrown,
Yeah, sure.
and that is
The
thermodynamics.
second law, especially, he was referring to.
Well,
but
the
in general.
entire thermodynamics. So thermodynamics is very, very important up to now, and nothing up to now seems to violate it. And it requires that the entropy be extensive.
So yeah, a lot of these paradoxes, keeping that in mind, that then applying it through non-additive entropy could give some solutions to this.
By the way, the professor that I was trying to remember his name 20 minutes ago is Michel Barranger
Okay,
from MIT, as I said.
great. I mean, these are fascinating.
who I think was a co-author of Feynman.
Is that right?
I think, yeah.
That's a
Michel Barranger.
good co-author. These are such fascinating stories. Maybe, if you wouldn't mind giving maybe one or two other examples. This was a fantastic one with black holes and cosmology.
For example, one that made us quite impressed was the applications that we found in the electroencephalograms of people, in particular of children. And one of my collaborators measured the electroencephalograms for different channels for a group of children, some of them typical ones, and some of them having the so-called attention deficit hyperactivity, which is the big problem for professors in primary schools.
Absolutely.
Because if in the room there is one or two, one is enough, one of these children, for the professor, it's very complicated to handle the lessons and the matter. So those are atypical children. So this collaborator, Dmitry Abramov, measured the electroencephalograms of, I think, 17 or 19 children, roughly half of them typical, and half of them having this, let us call it pathology. And by using Q statistics, we could show that through the encephalogram, we could detect if it's going to be typical or pathological. They appear in different places. So we could discriminate the two groups. In 100% of the cases, they showed different values of Q and of another parameter similar to Q, which we call C. So in the CQ plane, you have in different regions clusterized the typical children and the so-called pathological children. To make the diagnosis of a child being, say, having deficit attention and that kind of pathology, it's very complex to make the diagnosis. You need special psychiatrists or neurologists to make a lot of studies on the child, this and that, etc. And with our proposal, you just take an encephalogram on the child, which is non-invasive. The child has to be calm during 10 minutes, and then you get the electroencephalogram, and through the analysis that we do with Q statistics of that encephalogram, we can already make the diagnostic if it is typical or not. So we were perplexed to see the power of these analyses, which in practical terms is very easy to do, and in 100% of the cases it coincided with a diagnosis through the usual psychiatric manuals and codes.
So this is a simple quantitative test that can be done in comparison to a very complicated qualitative study
to determine if it is typical or not.
So that has really wide application.
Yeah, we believe.
What would be the next step? Are you able to do this in adults?
Well, we are right now starting a third paper on this, now analyzing typical adults and checking what influences the typical adults within this analysis. We have detected that the age matters and other quantitative properties matter, and we are just putting this in a logical frame
Really
to show what influences the complexity of the person. A living person is complex, is a complex system. A dying person is losing complexity. And there are studies of electrocardiograms, not electroencephalograms, but electrocardiograms, that some checking of the distances between the peaks in the electrocardiogram, if the fluctuations of those distances are Q Gaussians, with Q typically 1.4, the guy is fine. If the fluctuations approach Gaussian instead of Q Gaussian, when Q approaches 1, the guy is going to die.
This is other research that you've worked on?
We are not working on that,
That's something that you're familiar with.
but it is known.
Is this the heart rate variability? Is it related
Sorry?
Is this heart rate variability that they're talking about? Or?
Well, in those electrocardiograms,
Yeah.
there is a typical peak that appears,
Yeah.
and the distance between two successive peaks
Right.
is related to our heart frequency
Right.
that you can check through several methods. The distance between the peaks. But that distance between successive peaks is not constant.
Right.
It fluctuates around a mean value. So two peaks are a little bit closer or a little bit further away, and you measure the fluctuations of this, which you can measure easily once you have the electrocardiogram, and put the distribution of these fluctuations. If they are Q Gaussians, the guy is okay. If Q is approaching 1, that probably means that the central system is losing its correlation, its important correlation with the cardiovascular system. And when this correlation is lost, the guy dies.
He's going to die. Wow. It's quite fascinating. isn't it?
Yeah, if the correlations are okay,
Yeah.
then
Order is preserved within the system. Something like that.
I mean the living metabolism is working okay, and this happens thanks to strong correlations,
Okay.
which decay not exponentially quick, but power law quick.
Right.
And so Q measures this difference
Q Gaussian.
between strongly decaying correlations and slowly decaying correlations. Yeah, there are many papers showing that in the theory of finance, in the theory and in the experimental basis of those theory, it appears all the time non-additivity. I have myself published 3 or 4 or 5 of those, but there are hundreds of papers.
Sure. There's a lot of interest.
The first applications along that line were done by Lisa Borland and myself. And Lisa Borland was a postdoc. She's Swedish. And she spent 2 years in Rio de Janeiro, paid by the National Science Foundation of the United States to learn these concepts. And that was probably the first case in which United States was supporting somebody to learn something in Brazil, because along the entire history has been the other way around. Brazil supporting people that go in developed countries to learn things. That particular case of Lisa Borland was the other way around. She was along the 2 years she stayed with me at CBPF, she was supported by the National Science Foundation.
Interesting.
And now she works in a financial company in California.
In terms of a lot of what we're talking about, underneath that, your work is sort of inherently interdisciplinary. You're able to work with people from so many different fields. Part of this question is advice, because I'd like to know how to foster these kinds of collaborations better. But how does this happen? Do they contact you, or do you gain an interest and contact them?
With civil engineers from Catania, from the University of Catania, we have published 2 papers in which we show that the fractures, the microfractures, that ultimate can make the building to collapse down. These microfractures develop in a way following Q exponentials. And we plot the results in a representation where you have Q and an effective temperature.
Okay.
And according to whether the building or the tunnel or the monument or the bridge is getting risky, you see in those plots the points of Q and this effective temperature to approach the axis t equals 0. When those points touch t equals 0, the building collapses down. So by following where it is, you can say it's safe or it's not safe. This could have many applications in civil engineering, in the tunneling of a mine, or just the tunnels that exist in many cities. For example, here we have the Tunnel Rebouças, and it's a civil construction which can crawl down. So if you want to check if it is sure or not, if it is safe or not, you can do it through this procedure. And this happened because we were having lunch together in Catania, with two physicists and a lady who is a full professor of civil engineering in the same university. And while eating, we proposed to do this check. And then she made the experiments with cement, with basalt, with various construction materials, and she could measure the position of Q and temperature along this plot.
I see.
And in all those cases, when the curve touches t equals 0, and some non-trivial value of Q, the block, those were blocks of this size, big, through pressure, and when it achieved that point, the block broke down.
Very interesting. But in terms of the collaboration, is that common? Something kind of happenstance or spontaneous? Just the coming
Well,
together
you know,
of people?
chatting.
Yeah.
You say something, and the other one says something, and then you do something, and then somebody says, "Why don't we do this? And why don't we check it in the laboratory to see if it is true?"
Of course.
And this is how it happened.
Just think a bit more broadly with, as this has so much application, so many applications, somebody might be working in isolation somewhere and not even know this is possible. How do they know to think of you? Or how do you know, or somebody else that's working on non-additive entropy, how do they know about a problem that's being worked on that they can apply their theoretical knowledge to? I mean, are there any kind of advice that you know? Because you were able to do it hundreds of times, but maybe there's ways to foster
I
this
would
between
say
others.
people not to isolate too much.
Yeah.
Some degree of isolation is good to make your ideas more rigorous, to refine the details of those ideas. So some degree of isolation is good, but too much isolation makes you lose so many other things that would be useful precisely for what you are thinking about. So I would say a little isolation, but not too much isolation. There is an old Greek dictate from Cleovulos that was, I think, the 6th century before Christ, which is pan metron ariston. Pan, which means everything. This is where comes the word panorama. Pan. Metron, measure, metric. Ariston, excellent. So aristocracy, excellent. So everything in its measure is excellent. Not too much that way, neither too much the other way. But there is an optimum region in between. This is a very kind of general principle. So about isolation that you were mentioning again, not too much, not too little.
I think this is something that more researchers should be familiar with when they're addressing their problems, that perhaps as they're approaching it in a more traditional way or classical way or reductionist way, that maybe they should keep in mind that there's this alternative.
In fact, several people are introducing now non-additive entropies in the basic courses of statistical mechanics. I have done this several times in Brazil, but I have done it in Germany, in Turkey, in United States, and other people do that as well, like Christian Beck in Queen Mary's College, Ugur Tirnakli in Izmir, and many others. Andrea Rapizarda, that I mentioned to you earlier.
So the more acceptance, the more experimental verification there is, the more possibility of getting it introduced in an earlier stage in people's development.
Absolutely, yes,
Yeah.
absolutely.
That would be great. And I come to feel that way about complex systems in general. Like the more that approach seems like it could be taken in so many different ways, that if it's taught earlier, or if interdisciplinary approaches to knowledge are taught earlier, that there'll be more range, more flexibility in the mind of people to be able to come at problem names.
I think earlier is better.
Yeah, sure.
Yeah.
The earlier, the better.
For example, the additivity of Boltzmann-Gibbs entropy, I learned it when I was studying physics in Argentina. And to me it was like something not to be discussed. Entropy has to be additive. But then when you think again and again, then you come to questions, is it really always that the entropy is additive? Mm-hmm. Couldn't it be other cases in which the entropy is non-additive? And when you start thinking like this, you are already approaching a path which can make you generalize and unify lots of things that otherwise you wouldn't do.
Do you think there's the potential of this addressing some of the more foundational questions in science? To list a few, like origins of life, consciousness, the universe, cosmological origins, these kinds of like really big questions that are out there. Do you think there's the potential to address some of these questions by applying?
I think so.
Yeah.
To be concrete, some years ago, like maybe 6 or 7 years ago, I received a phone call from United States, from a foundation in the States, telling me that, listen, we want to support the development of studies of complexity in Latin America, and we would like it to be based in Brazil, and that you would be the head of this proposal in Rio de Janeiro. Mm-hmm. Are you interested? I said, yes. And they said, okay, then write down a white paper, a couple of pages. What would you do if the foundation gave to you $600,000 to do that along 3 years? So I wrote the paper and sent it to them. Mm-hmm. And a couple of weeks later, that person calls me back and tells me, I showed your stuff to the president of the foundation. Mm-hmm. He liked the thing, and I suggested that the foundation gives you not $600,000 but $800,000.
It's a good proposal.
So would you agree with that? I said, yes, of course. You can go on, no problem. And in fact, the money was given, and with that I hired several postdocs from different places around the world, and we did activities at the Latin America level for the students, but international level for the professors of those.
Yes. When was this?
Around 2016.
Okay, great. Recently?
Yeah, recently, yes. So they gave this money, they thought it could be well used. Mm-hmm. So I did my best to use it well, and a lot of things emerged from this support.
Absolutely. And going back to the question I posed to you about addressing some of these like bigger questions, foundational questions, was that part of the intention?
Yeah, absolutely.
So what were you looking at things like consciousness and origins?
Not specifically, but the idea was to relate with that kind of questions.
So there is the potential, it's being recognized even by financing systems, that these frameworks offer can address.
Yes, they spontaneously contacted me,
Yeah,
and they gave me $800,000
to do that and
to
bring
do
in
that.
people from that's fantastic.
Yeah.
Reminded, I have a colleague in Peru. I don't know if you know him, Enver Oruro.
Enver or
He works at he's a neuroscientist but works in complex systems, and he was just recently telling me that UNESCO was supporting him to head a Latin American initiative for complex systems,
well, you see.
something like this. So I mean, he's
Yeah.
he's a pretty young guy. I think maybe around 40, but yeah, just it reminds me, based on the story you're telling me, that
Yeah.
these are possibilities that are gaining recognition and can address some of the big problems in science, but perhaps, and I wonder your opinion, they can address some of the big problems facing humanity in different ways as well.
Yes.
What do you think? Because
I think it does.
social, environmental,
Oh, yeah,
these kinds of,
absolutely, yes.
so you see some potential there
Oh,
also?
yeah. Not only me, but many people see potential there.
But your opinion is very important to,
Yeah.
to me on this one. So
Yeah.
what do you think? How can these frameworks address
Well-
some of the complicated issues that we're facing in humanity?
Well, I mentioned to you that the rains in Sicily
Yep.
were well described by using Q exponential.
Yep.
And this is what Andrea Rapisardi is going to present in Erice in 2 weeks from now.
So hydrological patterns, for example.
Sorry?
So like complex dynamics of hydrology.
Yes, yes. There has been a book by an engineer from Texas that is called, the title of the book is Tsallis Entropy in Water Engineering.
Interesting. Okay.
And he explores the effects on rivers and other water systems,
So interesting.
as it is in the title of his book.
Absolutely. Yeah. So this is I mean, I've worked with some researchers here in Latin America around like nonlinear dynamics related to
Yeah.
water systems,
Yeah.
basin scale analysis, impacts of hydroelectric dams, and cumulative impacts, things like this. So you would say that non-additive entropy can be applied to this kind of analysis as well.
To several of those systems, yes.
So important.
It's hard to say that it is applicable to all of them,
That's so
but to big classes, surely yes.
Well, there's so many things in the world. I also wonder if it can, not just to address specific problems, but to create a more inclusive framework of collaboration and dialogue. Do you see these as possibilities to bring in expertise from different areas and address problems?
Well, for sure, because one thing is clear, entropy is a concept as important as energy, and they enter everywhere. So you have these concepts in engineering, in physics, in chemistry, in biology, in medicine. So for sure, that kind of interdisciplinary activities are well behaved if you use some more general concepts than the usual ones that are standard in statistical mechanics, in Boltzmann-Gibbs statistical mechanics, for sure. I have a friend with whom we are co-authors. We have published in Physical Review Letters Q generalizations of the Schrödinger equation, the Klein-Gordon equation, and the Dirac equation, based on the Q exponential, which generalizes the exponential. He likes to say, when nature likes a function, it uses it everywhere. And nature likes exponentials, sure. But it also likes Q exponentials.
Seems to.
So it uses them everywhere.
Seems to. Does this go towards, this is sort of another foundational question, universality of physical laws? Do you, I don't know how to ask, I mean, do you believe that physical laws are universal in this way, and that we're these sort of fundamental treatments of things like thermodynamics, that we're coming towards a more universal application of physical law. And would this be an example?
Hard to answer your question. It's a very difficult one. But in some cases, it is clear that it is so.
Yeah.
And the fact that the universality classes that have been introduced in physics, in the theory of critical phenomena, this concept is deeply related to the index Q and to the index delta. So these indices characterize universality classes of entropic non-additivity. I use very frequently the expression universality classes because you have an infinite number of systems that have Q equals, say, 0.24. So that value is a universal value for a whole class of systems. And this is why that expression, universality classes, is so familiar in the theory of critical phenomena, in the classical theory of critical phenomena. So universality class is a concept that appears very, very naturally there. I use myself many times the expression.
Makes perfect sense. And then going towards a recent publication of yours, what is it? Non-Additive Entropy and Statistical Mechanics at the Edge of Chaos, Bridging Between Natural and Social Sciences. This is kind of a review article where you show many of the different applications. Is this some of the belief that you're speaking to, that this can really cross the natural and social sciences?
In fact, that paper led to a natural collaboration between my daughter, who is a professor in psychology at the University of Rio de Janeiro State, and myself. So we could work together, and we devised an experiment which was applied to about 120 students to show that the learning or the memorization tasks of certain class occur not with Q equal 1, but with Q different from 1, which shows the importance in our minds, in our learning, the importance of long-range correlations.
Are we talking about like long-term memory, or what kind of learning? Because that can mean different things.
Correlations.
Like understanding.
It has to do with long-term memory.
I see.
But it is more general than long-term memory. And because of the relevance of these correlations, we arrived to the conclusion that it is because of these long-range correlations that humans can do metaphors, where you take some idea, some connection in one area, and you transport it to a completely different area, which has something in common with the primitive one, and this is a metaphor. So we coined the expression homo metaphoricus to indicate that humans are probably the only animals that do metaphors.
It holds such an important role in. I think I've mentioned to you that I've done a lot of work with traditional cultures, indigenous people. Their worldviews, their structures, which in many ways are empirical as well, they're transmitted through metaphors, like very profound metaphors. It's evidence of how important that is to the human element. So I think you're certainly right. It's very impressive once you sort of untangle the different levels of the metaphors and what they're actually representing in terms of the physical world, the environment that they live in. It's quite amazing. So that's fascinating.
Aristotle used to say metaphors of all things the greatest.
Is that right? Okay. Yeah. Well, still are. Maybe that's being lost in the information ecosystem that people live in now, the modern world. But for other, traditionally, it seems to be incredibly important. So that's.
Yeah.
So what are you finding with that? Are you going to take that any steps further with learning?
Not along that particular line. We published a couple of papers in collaboration with my daughter, but maybe, I don't know what is going to happen in the future.
I'm sure others will pick that up, though. That's really fascinating. Well, since some of these things, I would like to ask again if you've done any work or have any thoughts on the role of either complex systems or non-additive entropy towards consciousness. It's a big one, but just your thoughts, whatever you're comfortable with. It's a hard one.
Well, just let me tell you, because it's a very big and very hard subject, that it's hard to imagine consciousness without important correlations. Very hard to imagine.
Sure.
Since not that entropic non-additivity emerges when you have important long-range correlations, there are probably some aspects of consciousness that can be handled partially with entropic concepts.
As an emergent phenomena of
For example,
these systems.
yes.
So, I know it's a big topic, but just kind of to get your overall thought on that. Another difficult, foundational, big question that I want to research and treat in different ways on this new platform is the nature of time.
Nature of time.
Nature of time.
Yeah.
So another big one, but I mean, we can come at that from different angles. Thermodynamics and the causality and error of time, but just to even get your thoughts, I mean, do you see it as something more discrete or even fractal or scale invariant in structure, or do you believe in it more as like an absolute background dependent or something background independent as in general relativity? I'd just love to know what you think, because...
Let me first mention to you that Saint Augustine wrote, when nobody asks me about, I know what time is. But if they ask me to explain it, then I don't know anymore.
Clever response.
So I am pretty sure that time is not continuous. At the very fundamental level, at the Planck level, I would be very, very surprised that time is not quantified as so many other things in nature.
So
I think that it is discrete. But then if you ask me on what you base this belief, that's another story.
That's okay. I mean, a lot of people speculate on these things. I mean, do you see it as potentially multifractal or something that applies?
Something like that.
Yeah, or something that could, that non-additive entropy could be applied to in some capacity? Maybe. In terms of the reversibility
of time. Yes.
Of time and trying to uncover certain things related to causality as more of specifically thermodynamic treatment or something that's more foundational as well in terms of...
It was done on the basis of nonlinear dynamical systems.
Okay.
At a special point of nonlinear dynamical systems, a point which is precisely the edge of chaos.
Right.
In the chaotic region, you can predict nothing about the future. In the stable orbits, you can easily predict, because in the stable orbits, if something is up, down, up, down, up, down, I ask you, what's going to happen next? You're going to tell me up, down, up, down. And this is what happens. So in between this very unpredictable region, which is strong chaos, and the very predictable region, which is regular orbits, you have that special point, which is the edge of chaos, in which some degree of predictability appears to exist, in which you can partially reverse the future with the past and have the same behavior.
What are you hoping to uncover there in terms of causality or differences in terms of the reversibility that can show an arrow of time?
For sure, this must be related to causality, but I don't have clear ideas about that. It will be a fascinating area.
Absolutely. And then that can, in theory, show certain support for a thermodynamical arrow of time or reversibility using non-additive entropy that it,
Maybe, who knows?
yeah. It's such a fascinating topic. The other very big question, I suppose, is origins, in terms of origins of life. Do you see going from non-living to living, for example, any on Earth or anywhere, being able to uncover?
Biogenesis
Biogenesis
is a very interesting area also. Maybe like 30 or 40 years ago, I made a few papers with a friend and colleague who was, he left us by now, who was chemist, one of the most outstanding chemists of Brazil, Ricardo Ferreira. And we tried to present biogenesis as a phase transition, which we partially succeeded. And there were several papers along that line. And of course, it had an impact at the level of newspapers, because the origin of life is something that everybody would like to know something. But I have not thought about that particularly in terms of entropic non-additivity.
More phase transitions.
More phase transition. But since phase transitions are related to non-additivity, who knows?
Is this related to some of the, I guess, famed work of Stuart Kaufman and others? What you're talking about, the phase transitions and the biogenesis, or?
I don't remember. It was a kind of simple phase transition in which we tried to understand how oligomers, monomers, dimers get together and grow up in long molecules like DNA or proteins in such a way to be self-similar and self-replicating, which is the main characteristic of life. And this is along those lines that we worked in. But
how do you feel about some of these theories that use, at least in name, complex systems, that look at larger systems as living entities, like Gaia theory, for example?
Well, depending on what is your definition of life, it makes sense. Yeah, it makes absolutely sense. Because the Gaia idea is to present aspects of the Earth which are similar to the properties of living organisms. So if we have a big headache, this might make our heart to go faster, and this will have consequences in the way we breathe and the way we move, and all these things are related in very complex ways. And there are things in the Earth and in the planets in general that are similar. So depending on what do you call life, it's not a crazy idea at all.
Yeah, the self-regulating system, you know, essentially.
For example,
homeostasis, these kinds of things.
Yeah.
I find it really interesting too, and just it's a comprehensive way of explaining many things that happen or that humans are doing to the planet as well. So, but at least when I was in school, it was kind of, is this really a scientific theory? Is it not? But I think in terms of complexity science.
As I said, I believe that it is. It depends strongly on what do you call a living system.
Sure. Do you think that can be extended to an even broader scale, even on the scale of the universe, as looking at it as a self-regulating system? I know.
Maybe you can ask me something simpler.
Okay. Considering what the world is like now, so much polarization and misinformation, anti-scientific movements, what do those words mean for you? Science and evidence.
I think that's an important point. That even Plato was worried about that, and he used the expression episteme to refer to science, which is some sort of objective truth, as opposed to doxa, which is related to subjective truth. And this distinction is certainly very important nowadays when we see so many politicians and other people propagating all the time fake news. It's a terrible thing to happen, but they use it a lot. Goebbels used to say to Hitler, if something is false, you say that it is truth again and again and again and again, and finally it becomes truth in the mind of people, even if it is very false. And I heard that one of the people that Trump is going to indicate as minister in his administration declared recently, microbes do not exist. It's crazy to imagine that a country of 270 million inhabitants or something like that, like the United States, can have a minister that tells you in the 21st century microbes do not exist.
But people believe it, and they will believe it.
Some people tend to believe it. It's incredible.
How do you use science or objective truth, as you describe it, or some other model to fight against that kind of misinformation? How can science or any other kind of framework of dialogue address that?
Maybe try to convince at a child early stage to check things. So if somebody says microbes do not exist, call the child and put him in front of a microscope.
Okay.
And you see these things, what are these? This guy says that they do not exist, but you are seeing them, aren't you?
Critical thinking.
Critical thinking.
But the problem is that information, that's great if you can put them in front of a microscope, but if you tell them now in the world, go look it up.
Yeah, they don't go.
Or they go and it's full of misinformation or fake news or whatever you say.
So it's not an easy problem.
No, not at all. So I wonder that myself. How do you filter, or how do you know, or train people to look for things that have scientific integrity or evidence-based content?
Yeah,
What's that like for somebody in your position that's worked in so many disciplines and see people believing such nonsense now?
Yeah.
Must be challenging.
Well, Mach, the physicist from Austria, from his name, we call it as a unit of supersonic speed.
Right, sure.
For airplanes, 1 Mach, 2 Machs, etc. He declared in 1893, something like that, he declared in the Academy of Sciences of Vienna, I don't believe atoms exist. He was a very important scientist, very influential.
I think he influenced some of Einstein's theories.
Sorry?
I think some of his work influenced Einstein.
Influenced Einstein, but not that particular
not that
belief,
thankfully.
other beliefs. So it's terrible when such instructed and influential people can miss so much the truth, but it happens.
It's a complicated problem. Try to think how to address it. But for you, does, let's say in a pure sense, science, does it hold the potential as a sort of a pillar for...
Yes, but science which is open to alternatives and to criticism.
Right.
Because if science was monolithic and permanent forever, we wouldn't be here talking, because you wouldn't have airplanes to come to Rio de Janeiro.
Of course.
And you wouldn't have those electronic devices to register what we are saying. So science, yes, but it has to be an open science which admits the possibility of having some fundamental mistakes here and there and try to improve them.
Yeah, it's a dynamic process.
It's a dynamic process, yeah.
How do you get non-scientists to understand that? Because they look for certainty.
Well,
it's the education.
Education, yeah.
Thinking.
Try to convince them how hard and long is the process of discovering a truth.
Right.
So sometimes you make a mistake, and then if you're open, you want to correct it. So some people say, oh, there are so many billions of dollars supporting the studies of cancer. Why don't they find a final solution for cancer? But if that person had a little bit of training to see how hard it is to find the truth of something, then maybe he would have a different opinion.
Different view, of course.
Yeah, different view.
More respect. Do you think science itself, the definition of science, let's say, needs to be broadened? And I think of complex system science in particular. I mean, do you think there needs to be, within the scientific community, as you say, openness, but...
Yes.
I mean, as you know, as showing you this platform, I mean, more interdisciplinary thought, a broader definition. Do you think a broadening of what science means? I also think of empirical observation of communities, things like this, which may or may not be science, but it could be considered a kind of science, long-term observation. Do you think there's an importance of broadening what science is supposed to mean in order to get science to be more accepted?
I think the practice of science, if even a little progress along some scientific thing, the uncertainties, the errors involved in that process are very educational. So if you teach the young children to check things with that eye open about the possibility that maybe that path is slightly wrong or maybe very wrong, then I think you have done a big progress on the humankind.
But as you talk about introducing things like non-additive entropy to more introductory courses.
I was thinking earlier.
Yeah, even earlier, to introduce a way of thinking that's a bit more, seeing the correlations between different components or systems or things like that. Do you think that could help to foster more of an appreciation of the scientific process?
I think so. The practice of magics, where somebody does in front of you something that is amazing, then if you teach children to to do little things about magics can help them to understand how the appearance can differ from reality, and that it's easy to do for small children, and I think it helps later on to understand the more delicate issues like entropy or whatever else.
Do you think some of at least the core principles of something like complex systems should be taught to young children in school?
A little bit, why not?
Yeah.
Why not?
Just thinking a little bit more flexibly.
Sure. Why not?
What do you see the future of complex systems science like as it's maturing into a more established field, more global field, more centers of research? What do you think is coming?
Oh, well, the Nobel Prize in Physics a couple of years ago was given to people working in complexity.
Yeah.
So I see no problem about that.
Do you see a global expansion of this field of research, or do you see it touching many different aspects of things, or what do you see in the
Not
future?
really a global expansion, but for sure it's a perspective which can help to understand many systems, many things.
You would like to add?
No, just to thank you, your interest and the initiative that you take in doing all these things and that platform on which you are working. I wish you the very best.
I really appreciate that. Your work has been an inspiration, and I continue to look forward to seeing more of the amazing research you do. So thank you, Constantino.
My pleasure.
Thank you for joining us for this InterDialogue. You can subscribe to be notified of future episodes and by following us on our social media channels at the InterPlex. Visit our website, interplex.org, for more interdisciplinary and intercultural content and to join our growing collaborative community.